So I'm going to write two natural numbers on the board. So let's say 12 and 9. And we're going to have two players. Now the players take turn playing. Player 1 plays first. And the game goes on until someone cannot play. So our general rule is that whoever cannot play loses the game. Okay. Now, what can you do in your turn? In your turn, you can take one of these two integers and you can decrease it, but you have to keep it an integer. So it cannot go to 11.5, it cannot go to -1 and so on. And of course, the game ends when we reach 0, 0. Okay. So the player who cannot make a move loses the game. Who wants to play against me now? One volunteer. I'm going to pick a volunteer. You're the closest. Okay, do you want to be player 1 or player 2?
Player 1.
Okay, play. What do you do?
It's turn to 9.
Nice. Okay. So I'm going to decrease this one. He knows it. I'm going to decrease this one to 8. Okay, I'm going to decrease this to 7. Yeah, okay, I guess everyone got what's going on here. So he's just going to copy whatever I do. So let's say if I do 4, he's going to reduce this one to 4 and so on. And this game cannot go on forever. This game is going to end at some point because the sum of the two numbers is going down and it's a non-negative integer. It cannot go down forever. So eventually the game is going to end. But of course, I'm the one who's going to create the first 0 and he's the one who's going to create the second 0 and he's going to win. So at this point, I yield. Great. So for a game of NIM, with 2 heaps, this heaps is because originally when people were explaining this game, they were saying that you have a heap of beans and you can take beans from one of the heaps. Anyway, when you have 2 numbers and you're playing a game of NIM, assuming that both players play optimally, the winner really depends on whether the 2 numbers are equal. So if the 2 numbers are equal, player 2 wins. If the 2 numbers are not equal, player 1 wins. Okay. Great. But now I want to say, what are some properties of this game? Well, of course, it's turn-based, right? Which means that, well, players take turns playing it. The other property is that it's a finite game, in the sense that whenever I play this game, the play will eventually end, and it will take only a finite number of steps. It's also what we call an impartial game. And the idea here is that the set of moves that you have is really only dependent on which state of the game you're in. So it doesn't matter if you're player 1 or player 2. If it's your turn and you're starting here, you have the same set of moves, right? So for example, if you look at a game like chess, that's a partial game because what moves you can make actually depends on your color. Okay, so it's a turn-based finite and impartial game. And we also say that it has the standard winning condition. And the standard winning condition is that you win if your opponent cannot move, or you lose if you cannot move. Okay. So for the case of 2 numbers, we saw very easily what the best strategy is going to be. But what happens if I have more than 2 numbers? So let's say I have 5, 7, and 12. Okay, who wants to play this one? Not you again, you know the strategy. Do you want to play? Do you want to be player 1 or player 2? Okay. What do you want to do? 10 to 7 to? Oh, 5 to 0. Nice. But then the problem with this is that we're back into the case with only two numbers. And I'm the one who's going to win that because I'm going to make this 7, 7. Okay, so I'll give you another chance. Or 7, 12. I'm not going to play optimally, by the way. So let's say I turn this into 4, 7, 7. What would you do at this point? No. If you have 4, 7, 7, you can get rid of the 4, right? You can turn the 4 into a 0. If you turn the 4 into a 0, then we're left at 7, 7, and then from here you can win. Okay. So I'm going to give you another chance, and I'm going to give myself another chance. We're backtracking on this game. So we are at 4, 7, 12. Let me see. I'm going to turn this into 4, 7, 11. I'm gonna turn it into 4, 6, 10. Not necessarily. 4, 6, 9. Okay. Nice. Let me do 4, 6, 8. I'm giving you a lot of chances to win this game. Four, 6, 4. Okay. Finally, at this point, you're winning 4, 0, 4, and then you. Nice. Okay. But let me again backtrack. So instead of 4, 6, 4, what if I did 4, 6, 6? 2, 2, 0, 6, 6. Yes. So let me see, what else can I do? Actually, I could do this, right? I could do 4, 6, 0. Then you should do 4, 4, 0. Yes. What if I do 4, 6, 1? Okay. Now I do 4, 3, 1. 4, 3, 2, 1. Oh. 1, 2, 1. Oh no, that's a bad idea. If you do 1, 2, 1, I would do 1, 0. Yeah, but at this point there's nothing else really, right? So say 1, 2, 1, I do 0, 1, and finally I win. Okay, Did you see a strategy? So there is actually a strategy hidden in there, and I didn't play it well because I'm too lazy to calculate the optimal strategy every time. But let's try to find it out. Okay. So first of all, I'm going to model these games as graphs. So let's say I create a graph, and in this graph, I put one vertex for every possible state of my game. So in this original game, I have, what, 13 times 10, 130 states, right? In this one, I have way more. But in general, suppose that, I mean, I can use a computer, so it's fine. I can just create a huge game. So whenever I have a game that has these properties, term-based, finite, impartial, and so on, I'm going to create a graph. And basically, I'm going to say I put one vertex for every state of my game. And then I put an edge from a state to another state if the player can move from here to here in one turn. Okay. So what kind of graph will I get? Yes, it's going to be a DAG. Why is it going to be a DAG? Well, of course, it's directed, but why can't I have a cycle? Yes, because we said that every play of the game is finite. If I have a cycle, I can just keep going through the cycle. Of course, it requires the collaboration of the two players, but it is possible to have a play of the game that goes on forever. So we cannot have a cycle. So let's say this is my game graph. I want to see what are the states from which player 1 would win, and what are the states such that if I start there, player 2 would win. Okay. So I define these states. I say a state is winning, or W. Let's give it a name. So I would say a state V is winning if when we start the game at V, player 1 wins. And I say a state is losing if player 2 wins. And I show it with L, if when we start at V, player 2. So basically, I'm looking at everything from the point of view of player 1. Okay. First of all, this W and L, we can think of them as sets of states. And I'm going to claim that W union with L is the set of all vertices in my graph. So basically, I'm saying no matter where I start, either player 1 is going to win or player 2. Now, this is a theorem that I leave for you as an exercise. It's quite easy to prove. Okay. But again, just think about it. It's not possible that no one wins and both of them are infinitely smart. They're not making any mistakes. But actually, another way of proving this theorem would be to try to figure out exactly which vertices are W and exactly which vertices are L. Okay. So let me actually add some extra vertex here. So first of all, I want to look at the vertices that have no outgoing edges. And I have such a vertex because this is acyclic, right? Because we've proven this before. If every vertex has at least one outgoing edge, we have a cycle. And the proof was that you just start somewhere, keep taking the outgoing edge, right? Eventually, you'll have to get back to a vertex you've already seen. Great. So I take one of the vertices that has no outgoing edges. Is this a winning vertex or a losing vertex? It's a losing vertex. So this one is also a losing vertex because, of course, if I start my game at any of these vertices, there is no move for player 1, and by definition, the player who cannot move loses the game. Okay. Now, how about this vertex? What can I say about this vertex? Well, you know, at this point, I don't really have losing or winning assigned to all of its successors. So maybe it's too soon to decide about this one. How about this one? I can decide about this one, right? Is this a winning vertex or a losing vertex? Why is this a winning vertex? Yeah. So the idea is, suppose that I start the game here. Player one would just take one of the edges that go to a losing vertex. And then the losing state is basically given to player two, right? Because now player one has moved, so the role of the players has switched. So player two is the one who's going to lose. So player one is going to win. Okay. Now, let's go back to this state. Is this a winning state or a losing state? It's a winning state. Because if we start the game here, player one can go here and then player two would lose, or player one can go here and player two would win. But we said our players are infinitely smart. So this is the definition of a mistake. Player one would never take this edge. Right? So this is a winning vertex. Great. Now I can continue like this. What about this one? Is this a winning or a losing vertex? This is a losing vertex. Because if you look at it, suppose I start my game here. Player one has the option of taking this edge and then player two will win, or taking this edge and again player two will win. So no matter what player one does at this point, player two is going to win the game. So this is a losing state. Okay, how about this one? This is a winning state because player one would just go to the losing state and give that to player two. How about this one? This is also a winning state because player one can just go here. Okay, so what is the rule? The rule is that a vertex is a winning vertex if it has at least one losing successor, right? But if all of the successors of a vertex are winning, then that vertex is losing. Okay. So I also have a base case, which is the case where the vertex has no successors. So these are my rules. Rule 0, which is my base case, is that if V has no outgoing edges, then V is losing. My rule 1 is that if there exists some vertex U such that V has an edge to U, so if I want to be more formal, it means that VU is in E and U is a losing vertex, then V is a winning vertex. Okay. And finally, my rule 2 is that if for every U such that VU is in E, we have U in W, then V is in F. Okay. Now, question. Why can I always apply these rules to assign W or L to all of my vertices? This is the same as proving this, that W union L is going to be B. So why do I never get stuck when I'm assigning W and L using these 3 rules? So when I told you about rule 0, I told you that I can at least use it once, right? Because there is going to be a vertex that doesn't have an outgoing edge. Okay, but that's not enough, right? I want to say that I can use my rules repeatedly to assign either W or L to every vertex. And then, of course, I have to prove that this assignment is unique. Like I don't put any vertex in both W and L, but that part is quite trivial. So when can I assign W or L to a vertex? I can assign it only when I'm already done with all of the successors. Right? So whenever I'm done with all of the successors of this vertex, I can assign it. Of course, in some cases, I can assign it sooner. For example, remember when I assigned W here, I had not assigned anything here, but because I already had an L, I could just say, okay, this is a W, right? But let's be really stringent, and let's say that we assign W or L to a vertex only when all of its successors have already been assigned, okay? I claim that there is an order for doing this such that I assign W or L to every vertex. Or another way of looking at this is that I have a permutation of my vertices such that the successors of every vertex appear before that vertex. Now, we usually do this in the other way, and that's the definition of a topological ordering. Topological order, the idea is this. Given a graph, let's say it's a directed acyclic graph, G, VE, a topological order, it has nothing to do with topology, by the way, is a permutation of vertices. So it's a permutation P of vertices such that for every vertex, or I can say it like this, such that for every edge E, which goes from U to V, the vertex U appears before V in P. Okay. So, okay, this is like the standard way of defining topological orders, and it's kind of the opposite of what we want, right? So it says that whenever I have an edge from U to V, U should appear first. But actually what I want here is an order such that whenever I have an edge from U to V, V appears first. Doesn't really matter, just reverse all of your edges, right? So if I prove that the topological order exists, I've proven that this order that I'm looking for here also exists. It's just a topological order in the reverse graph. Okay. Give me a proof. So this is the theorem I want to prove. I want to say every DAG has a topological order. First of all, of course, if I have a cycle, I don't have a topological order, right? Because if I have a cycle, every element in this cycle should appear before the next element, but it's a cycle, so I cannot do it. But what I'm saying here is that if my graph doesn't have a cycle, if it's a DAG, then it definitely has a topological. Yes. But I just wanted to do this again here. So the idea is very simple. The idea is that I'm going to have an algorithm that gives me a topological order. I'm going to do one vertex at a time. I'm going to take a vertex that has no in degree. For example, this vertex, there's no edges coming in. I'm going to put it at the beginning and remove this vertex. Then again, I'm going to pick another vertex that has no incoming edges. This one will not have incoming edges when I remove this one. So then I can put this one, and I can keep doing this. So every DAG has a topological order, and then I can use this theorem to come back and prove that this one also holds, because I just have a topological order of the reverse graph, and then in that order, I'm assigning L and W to everything. So whenever I'm processing a vertex, I'm sure that I have already assigned L or W to all of its successors. So I just look at the list of successors. If there is an L somewhere, I say this vertex is a W. If there is no L anywhere, I say this vertex is. Okay, great. But you see the problem. The problem is that I will have a lot of states. So in this case, again, I will have my first component, which can go from 0 to 12, and my second component, which can go from 0 to 10. So I have 130 states. In this case, I have 6 times 8 times 13 states. Right? In general, this is not something that I'm too happy with. So usually I would not want to create this graph because this graph would be too big. I will have one vertex for every state. But I can still use the reasoning based on these rules, right? So what do I want to do here? I want to basically take all of my states and I want to divide them into two sets, W and N. And these two sets should satisfy these three rules, right? Because I've shown that there is also a unique division to W and L such that they satisfy these three rules. So instead of actually creating this whole graph and doing the algorithm on it, I'm going to just use combinatorial means and I'm going to figure out what is the set of states that are W and what set of states are N. So for example, here, in the case where I had only 2 heaps, what can I say? I can say L is the set of all states of the form XX. And I can say that W is the set of all states of the form XY, where X is not equal to. And you can easily check that they satisfy all 3 of these rules. So if I have no outgoing edges, what does that mean? That means that I'm at 0, 0. So 0, 0 should be in L and 0, 0 is in L. Now, if I take a state in L, all of its successors should be in W. If I have a state in L, the 2 numbers are equal. When the player moves, one of the numbers changes, so they're no longer going to be equal. So all of my successors are going to be in W. If I take a state in W, there should be at least one successor in L. But there is. I mean, if I have 2 numbers, X and Y, and they're not equal, as the player, I can take the bigger one and reduce it so that it becomes equal to the smaller. Okay. So very easily, I could just prove that this is the losing set and this is the winning set when I have NIM with 2 heaps. But what happens when I have NIM with 3 heaps? So this one. Or in general, what happens if I have NIM with n heaps? So this is the general case of NIM, is that we have n numbers. And again, these are natural numbers. Let's call them A1, A2 to AN. And they're all natural numbers. And each player can choose a number and decrease it in their turn. So again, what I want to do is to come up with a definition for the 2 sets, L and W, that satisfies the 3 rules we've seen before. Okay. Now, this is one of the most interesting things that has happened because this is a theory that was kind of independent of computer science, but we have XOR in it suddenly. So here's the thing. If I write 2 numbers in binary, I can define their bitwise XOR, right? So let's say I have 2 numbers, for example, 4 and 7. I can write these in binary. So what is 4 in binary? It's just 1, 0, 0. Right? What is 7 in binary? So it's this. Now, I can take the XOR of these two. And what I mean is that I just compare every bit. And if that bit is the same, I put a 0. If that bit is not the same, I put a 1. Okay. So you can think of it as just binary addition, except that I don't carry anything to the next digit. Okay. So 0 XOR 1 is 1, 0 XOR 1 is 1, 1 XOR 1 is 0. Okay. And of course, it's called exclusive OR because it's like taking the OR, but also it's 0 when both of them are 1. It's exclusive, like not both at the same time. Great. So here's what I want to claim. I want to claim whether we are in a winning state or a losing state is dependent on the XOR of all the numbers. Okay. So I'm going to have two sets. One is going to be my winning state. The other one is going to be my losing state. By the way, sometimes we show XOR like this. Okay. So I'm going to have a set, and I'm going to say this is the set of all A1, A2 to AN, such that the XOR of all of them is 0. And then I'm going to have another set, which is the set of all A1, A2 to AN, such that the XOR is not 0. Okay. Suppose that I want one of these sets to be my winning set and the other one to be my losing set. Which one should be the losing set? Remember our rule 0. Our rule 0 is that if we cannot move, we should be in a losing state. So when can we not move? When all of them are 0. But if all of my numbers are 0, then their XOR is also 0. So if I want to divide it like this one has to be L. And this one has to be W. Okay. But let's see if this definition works. This is just like a guess at this point. Right? I have to actually prove that it also satisfies the other two properties. So I've proven that if I cannot move, I'm in a losing state, I'm in L. But I have to prove these two as well. I have to say that whenever I'm in W, I have an edge or a move that goes to L. And whenever I am in L, no matter what I do, I will end up in W. Right. The second one is easier. So let's say the XOR of all of my numbers is 0. And I change one of the numbers. Why can't the XOR remain 0? Okay. So this is like this. I'm saying that suppose A1 XOR A2, so on to AN, the XOR of everything was 0. And I'm going to change one of these numbers. Okay. And let's say the player changes one of them, for example, AI to A prime I. Why is the XOR no longer 0? Well, one thing you can do with XORs is that you can just move your numbers around like in addition, except that you don't really have negative numbers here. So if I have, for example, A1 XOR A2 XOR A3 is 0, I can also say that this means that A1 XOR A2 is equal to A3. Right. Why is that? Well, first of all, XOR is associative, so the order doesn't matter. Basically, to see that, you can just think of every bit. In every bit, I'm just counting, is there an odd number of numbers that have a 1 in this position or an even number of 1s in this position, right? So the order here doesn't matter. So I can say something like this. I can order it like this. some number XORed with A3 is 0. That number has to be A3. Because the only way you can get something XORed with A3 to be 0 is to XOR it with itself. Okay. So it's a very simple thing. Now, this also applies to XORing more than 3 numbers, of course. So if the XOR of A1 to AN is 0, and then the player changes AI to A prime I, what do I know? The XOR of all of them was 0, so I just move AI to the other side. So I have that AI is A1 XOR A2 XOR blah blah to AI minus 1, and then I don't have AI itself, but I have AI plus 1 XORed all the way to A. Right. Okay, but now I'm changing A1 to A prime, sorry, AI to A prime I, but I'm not changing any of the other ones. So this XOR is going to remain the same, but I'm changing this AI to A prime I. So it's not going to be equal to this XOR. So if the XOR of all of my numbers is 0, no matter what I do, no matter what move I make, the resulting XOR will not be 0. Okay, so this proves that whenever I'm in a losing position, whenever I'm in L and I make one move, I'm definitely going to end up in top. But now I have to prove one other thing. I have to say whenever I'm in W, there exists a move that moves me into L. Okay, that's actually kind of harder. So let A1 to AN be a state in W. What does this mean? It means that the XOR of all of them is not 0. We want to say that there exists a move that makes the XOR 0. There exists some index I and some value A prime I less than AI, such that this XOR, if I use A prime I instead of AI, would be 0. So this is just the XOR of J from 1 to I minus 1 AJ, XORed with the XOR of J from I plus 1 to N AJ, XORed with AI prime. This whole thing is 0. Okay. Why is this always the case? I have a bunch of numbers, their XOR is not 0. Why can I always reduce at least one of them such that the XOR becomes 0? So let's go through this example, for example. Let's write 5, 7, and 12 in binary. So I have 5, 7, and 12. What is 5 in binary? It's 4 plus 1. So I have 4, I don't have 2, I have 1. Okay. What is 7? 7 is 4 plus 2 plus 1. What is 12? It's 8 plus 4. So these are my numbers in binary. Okay. Now, if I take their XOR, this one is 0, this one is 1, this one is 1 because I have an odd number of 1s, and this one is also. So what is this XOR? It's 12 plus 2 is 14. Why can I always make the XOR equal to 0? Well, let's look at every bit in my XOR that is 1. And let's see how I can turn it into a 0. So this bit here is 1. How can I turn it into a 0 if I change this one to a 0? Right. But if I do this, remember, I can only change one of my numbers. So I'm changing 12. And this means that I have committed to changing 12 now. I cannot change any other number. Whatever I mean, I can decide how much I'm going to subtract from 12, but now I cannot touch 5 and 7 anymore. But I didn't have a choice here. I had to choose 12 because I have a 1 in this bit and I want the overall XOR to be 0. So I have to turn this into a 0. So I have to take something from 12. Okay. This bit here is also 1. So fortunately, I have a 1 here. So if I turn this one to a 0, then this one will also become a 0. Okay. This bit is also a 1, but I only have a 0 here. Now, going from 1 to 0 was fine because that's decreasing the number. Is going from 0 to 1 also fine? In this case, yes, because look, if I change this from 0 to 1, what does this mean? This means that I'm adding 2 to my number, but I've already subtracted 4 here and 8 here. So the number is going to still decrease. And then this one is already 0, so I'm fine. So what did I do here? I changed the 12 to 2. Right? And you can easily check that 5 XOR 7 XOR 2 is 0. Okay. Now, I want to say that I can always do this. Why can I always do this? Let's consider a situation like this. Let's say that I write all of my numbers in binary. So I have A1, I've written it in binary, I have A2, so on, up to AN. All of them written in binary. So this is the binary representation. I'm not going to actually write it. And then I have the XOR result. So I have whatever, 1, 0, 1, 1, 0, 0, 0, 1, 0. Okay. I want this XOR to become 0. So I just actually, let's say it starts with a bunch of zeros as well. So I'm going to take the first bit, the most significant bit, that is 1. What does it mean when this one is 1? It means that if I look at this column, if I look at this same bit in all of my numbers, an odd number of them had a 1, right? So if an odd number of them had a 1, that means that at least one of them had a 1, right? I'm going to pick any number that had a 1 here, and I'm going to say this is my AI. Okay. Now, here's what I'm going to say. I'm going to say, let's take this 1 in AI and reduce it to 0. That would make sure that this bit becomes a 0, right? But then I'm going to make a bigger claim. I'm going to say that in my number AI, after this bit, I can write whatever I want. Why is that the case? Because suppose that this was the J's bit. Okay. When I changed it from 1 to 0 in AI, I reduced AI by 2 to the power of J. Now, if I change all these remaining digits, all the digits to the right, they're going to basically add or subtract values that are 2 to the power of things that are smaller than J. Right? So this one is 2 to the power of J minus 1, 2 to the power of J minus 2, and so on. But the sum of all those powers of 2 is less than 2 to the power of J. So no matter how I rewrite this part, my number is going down anyway. Okay, great. So now I can just go through this list and I can make sure that everything here happens to be 0. So here's the thing. If I have a digit that is already 0 in my XOR, I do not change it here. I keep it what it was, right? Because this means that in this column, I already had an even number of 1s, and I'm happy with that. I'm happy with having an even number of 1s. But if I see a 1, I just change whatever I had here. If it's a 0, I turn it into a 1. If it's a 1, I turn it into a 0. That makes sure that this one becomes 0. And I keep doing this until my last digit or first digit, depending on which side you look at. Okay. So this shows you that I can always change only one of the numbers, decrease only one of the numbers, such that the XOR of all the numbers becomes 0. Okay, great. So I proved that this definition of W and L, where L is the set of all states where the XOR is 0, and W is the set of all states where the XOR is non-zero, satisfies these three rules. Right. And we've seen that this gives us a unique solution. So it's the unique division of states that satisfies these rules. So it's actually my winning and losing states. So now if I give you a name with any number of heaps, any number of integers, you know how to put it. Okay. But this is interesting because let's look at it again from the point of view of this graph. So if you think about it, what is NIM? What are the graphs that we have in NIM? So let's say I have, for example, 5, 7, and 12, right? What if I only had 5? What if my number, what if I had just like one heap and it was only 5? What would my graph look like? It would be something like this, right? I have 0, and then I have 1, which has an edge to 0. I have a state for 2, which has an edge to 1, and another one to 0, and then 3, 4, and 5. Right? And each one of them has edges to everything to its right. Okay. And I could create the same thing for 7 and for 12. So let's consider this graph and let's call it G5. Let's call the graph for 7 G7 and this one G12. When I have two numbers, when I have both 5 and 7, what is the graph that I'm playing on? It's just G5 times G7, right? It's the Cartesian product. And when I have three numbers, it's just the product of all of them. So if I have three numbers, 5, 7, and 12, the graph I'm actually playing on is G5 times G7 times G12. Okay. Which is, again, a huge graph, right? But I could create this graph and I could apply this algorithm, finding a topological order and finding L and W. And of course, it would give me the same result. It would give me the same set L and W that I found here. But what's interesting to me is whether I can actually extend this to other graphs. So let's say, instead of just giving you one graph, as here, I'm going to give you two graphs. And I'm going to say that my game is going to be played on the product of these two graphs and give me the winning and losing sets. Okay. What does it mean to say I'm playing on the product of two graphs? Well, it's kind of like this. Let's say I have this graph. I'm going to remove the winning and losing stuff here. Instead, I'm going to just add some vertex labels. So 1, 2, 3, 4, 5, 6, 7. Okay. And let's say I have another graph. Just to make it easier, I'm going to remove 6 and 7 here. Can be really any graph. But let's say this is my other graph. Okay. Now, what I'm telling you is this. I'm telling you that you're going to have a pebble or a token originally put on each of these graphs. And let's say both of them start at vertex 1. So I'm going to have a token here and I'm going to have a token here. And we're going to play a turn-based game. In each turn, the player can move one of the two tokens, not both of them. And the player who cannot move loses. Now, I want you to tell me for every combination of starting vertices, which player has a winning strategy. Okay. So why is this the product graph? Well, we can just take a look at what this is. So let's say this one is G1, which is V1, E1. And let's say this graph is G2, which is V2, E2. Okay. What are the states of my game? So let's say my game is also, of course, a graph with vertex set V and edge set E. But what are the states of my game? It's going to be a pair of vertices, one vertex in G1 and one vertex in G2, right? So my V is going to be V1 times V2, Cartesian product, right? What is my E? What are the edges that I have? So when do I have an edge from U1, U2 to, let's say, V1, V2? Well, I said that in every step, the player can either move in the first graph, which means that the second component remains the same, or they can move in the second graph, which means the first component remains the same, right? So my set E is going to be this. If I move in the first component, I will go from a state UV to another state UV prime, right? Sorry, if I move in the second component, where V and V prime, this edge is in E2. Union with the case where I move in the first component. So I go from the state UV to a state U prime V, where U prime is in E1. I'm just writing the definition of the Cartesian product of two graphs. So this is exactly what we're doing. Now, of course, if I want to find the winning set and the losing set in these two games, I can just compute this graph, and then I can apply my algorithm on this graph. One by one, I take my vertices, I decide if they're winning or losing based on the topological ordering, and I'm going to get an answer. But of course, you see that this is not efficient. And especially if it's not efficient if I have many more components. It's actually going to take exponential time. So if I have, let's say, actually, let's say all of my components are small. Let's say all of my components have a size of 5, right? If I have n components, I have 5 to the power of n states. That's so big, we can't even solve it with computers for large n, right? But again, if you look at the case of NIM, we had something similar here. I could think of NIM as a game on a graph as well, and it's also a very specific type of graph. But I never really created G5 times G7 times G12. I just directly found a rule that told me when I win and when I lose. Now, what I want to prove is that every game is kind of like NIM. And basically, I want to say that in the same way that you can find winning rules for NIM, you can find winning rules for any game. Okay. Now, here's what I want to do. By the way, this is called the Sprague-Grundy theorem. I want to say I take every vertex of each one of these two graphs that I have, and I'm going to associate it with a NIM heap size, with a number in NIM. And then I want to say that when I'm playing this product game, I'm going to think of it as a game of NIM. I'm going to think that, well, I have a NIM number here. Actually, instead of NIM number, people say NIMBER. I have a NIMBER here, and I have another NIMBER here, and I'm going to just pretend that I'm playing NIM. So in my mind, I'm going to simulate NIM while I'm playing this other NIM. Okay. But the problem is that I have to have a way of assigning numbers to each one of my vertices. So I want to say that, for example, when I'm at this vertex, I think of it as having a number of 2, right? That's what I want to do. So let's try to assign numbers to vertices, and let's see how this goes. If I'm at this vertex, I cannot do anything, right? So if you only look at G1, if I'm here, I'm stuck, right? So if I wanted to think of this as a heap in nim, it would be a heap of size 0, right? Because that's the only case where I cannot make any moves. Okay. This one will also have a number of 0. Okay. Now, if you look at this one, vertex 5, with one move, I can turn it to a state that has a number of 0. So this kind of looks like the number 1 in nim, right? Because in nim, it's only the number 1 that can, with one move, be converted only to 0. Okay. Now let's look at this vertex 4. With one move, I can turn it into a number of 0 or a number of 1. So this one looks like a 2. Okay, so I'm going to assign a number of 2 to this one. Okay. How about this one? If I look at vertex 3, what's going to happen there? So with one move, I can turn it to a number of 1 or a number of 2, but I don't have anything like that in nim, right? Because in nim, of course, I have the number 3, but I can also turn it to 0. Here, I don't have any move that turns it to 0. Okay. But here's the thing. Was this a winning vertex or a losing vertex in the original game G1? It was a losing vertex, right? And in nim, the only value that I can assign to a losing vertex is 0. So I'm actually going to assign a number of 0 to this one. Okay. Now, let's look at this one. This can be converted into 0 or 2 with one step. So actually, I'm going to assign a number of 1 to it. The rule is that I'm going to assign the smallest number that does not appear in any of the successors. Okay. So if I look at the successors of this vertex, I see 0 and 1, so I'm going to assign 2. Okay. So this is what I'm going to do now. I assign a number to every vertex in each GI. Okay, in each of my components. So I'm looking at each component separately. And what I'm doing is very simple. Again, I'm going to have 2 rules. Rule 0 is that if V has no outgoing edge, then the number I'm assigning to V, I'm going to write it like this, is going to be 0. Okay. And my other rule is that if V has outgoing edges, has edges to, let's say, U1, U2 to UK, I'm going to say that the number of V is actually, the notation they use is this, is max of the numbers of U1, U2 to UK. And what this means is the smallest number that is not in this set. Okay. So max of A is basically the minimum element of A complement. Okay. Let's do this in this graph as well. So in this graph, 4 is getting a number of 0, 5 is getting a number of 0, 3 gets a number of 1, 2 gets a number of, oh, I have to go here. 1 gets a number of 2, right? And 2 gets a number of 3, because it has 0, 1, and 2. Okay. So up until this point, this doesn't seem to make a lot of sense. I'm just having a way of translating vertices in any graph to numbers. But now this is the great claim. I claim that a state is a losing state if the XOR of the numbers is 0, and it's a winning state if the XOR of the numbers is not 0. Okay. This is the Sprague-Grundy theorem. I say that my losing states is the set of all states V1 to Vn such that the XOR of the numbers of the VIs is 0. And my winning state, my set of winning states is all the states such that the XOR of the numbers is non-zero. Okay. Why is this? Again, intuitively, the way I'm thinking about this is that I have translated every vertex of each of these graphs to a number. So even though I'm playing on these graphs, I'm going to pretend like I'm playing nim. Okay. So I start and I look at the XOR of the numbers. If the XOR of the numbers is not 0, I have a way of making them 0, right? Because remember, this is again the same theorem here. I can reduce one of the AIs. These AIs are now my numbers associated to vertices. I can reduce one of them such that the XOR becomes 0. But the way I assign numbers makes sure that if I have a number of 3 here, for example, I have a way of reducing it to 2, I have a way of reducing it to 1, and I have a way of reducing it to 0. So every move that I have in nim, I also have in this game, right? So if I want to reduce some number from, let's say, 5 to 2, I definitely have an edge that goes from the corresponding vertex that has number 5 to a vertex that has number 2. Because whenever I have number 5, I definitely have edges to 0, 1, 2, 3, and 4. Okay, great. But there is a problem. This is not exactly a one-to-one correspondence, right? So for example, suppose that I am in the state, okay, let me erase this one and this one. And let's see. What state do I want to be in? So remember, this was vertex 1, this was vertex 1. Okay, let's say I'm in this state. I'm in 3, 2. Okay. So if the tokens are in these red places, and let's say it's player 1's turn, player 1 can move from here from 3 to 4, right? But this is not a move that exists in the corresponding nim game, because in the corresponding nim game, this is a 0. I'm going to 2, right? So this is a problem. It seems like even though any move that I made in the corresponding nim game, I can also make it here. The opposite doesn't hold. I have some moves here which I don't have in the corresponding nim game. I claim these moves don't matter. Why don't they matter? Why doesn't it matter that from here the player can go here and increase the value of the nim? I'll give you a second to think about it. Yeah. So suppose that I'm player 1 and I increase the number. Player 2 can just decrease it back, right? So this is a nonsense move. I can go from 0 to 2, but because this is 2, it has an edge to a 0 somewhere, right? So player 2 can just undo my move, can get me back to a number of 0. Okay, so that's the reason why these moves don't matter. Great. So that's the proof, actually. That's all you needed. You're just simulating NIM.
PR always PR may be no way to lie.
Yes, but again, we're assuming that both of the players are infinitely smart, right? So here's the thing. Suppose that I'm in some state, and suppose that based on the numbers in the corresponding game of NIM, I'm winning the game. So I would just make the winning move in NIM, right? So the only case where I would make a move like this, going from some number to something bigger, is if I'm losing the game, right? But that's not going to help me win the game, because if I do this, then my opponent just undoes what I did. Okay. But very importantly, this only holds for finite games. I shouldn't be able to increase the number forever, right? This works because we're saying that the game will eventually end. So yeah, I can increase the number, but then my opponent decreases it back to the same place. And yeah, that's it. Great. I can, of course, argue this directly based on these sets, right? So these winning and losing sets have to satisfy my 3 rules. These 3 rules for winning and losing sets. So first of all, if I have a state that has no outgoing edge, so V1 doesn't have any outgoing edge in G1, V2 doesn't have any outgoing edge in G2, and so on. So all of them get assigned a number of 0. This is because of this. So the XOR is 0. So the first condition is satisfied. If someone cannot move, they're in a losing state. If I'm in a losing state, I claim that whatever move I make is going to get me into a winning state, right? Now, why is that the case? So I'm claiming that any move I make is going to be one of 2 forms. It's either going to increase one of the numbers or it's going to decrease one of the numbers. If it decreases one of the numbers, it's the same argument as in NIM. The XOR is 0, I'm decreasing one of them, it's no longer 0. But the same argument also works if I'm increasing. As long as I'm changing one of them, I have a bunch of numbers, their XOR is 0, I'm changing one of them, their XOR is not going to be 0. Right? Can I have a case where I change my vertex, but its number doesn't change? That's the case that's the corner case that you have to check. Is it possible that my number doesn't change? No. That's because of this definition, right? So basically the idea is this. Suppose that I'm at this vertex, and let's say this one has number k and this one also has number k, right? What does it mean? It means that this one has edges that go to numbers 0, 1 to k minus 1. This one also has edges that go to numbers 0, 1 to k minus 1. Okay. If this one also had an edge to this one, then it has edges to 0, 1, k minus 1, and k, so it should have number k plus 1. Right. So this can never happen. That's the only corner case that I had to check. Okay. The other case is much easier. The XOR of all of my numbers is not 0, so I have one of these numbers such that I can decrease it so that the XOR becomes 0. I just find the corresponding move in the graph. Okay. Great. So this means that whenever I give you any kind of graph game like this, which has many components, you can just solve each component separately. And after solving each component separately, you can take the XOR of all, the XOR of the numbers of all. And Another interesting thing is that, of course, there is a relation between the L and W's that we wrote here and the numbers that we wrote here. And the relation is that the zeros are L's and the non-zeros are W's. So all our losing states are zero, have a number of zero, but winning states can have different numbers. But this only works if our components are completely independent of each other. It's basically that I'm playing the product of two games or several games. I have several games. In each turn, I can choose one of the games and make a move only in that one, right? If my two games are somehow related to each other, I cannot use this. So here's an example. So suppose that I have two numbers. We have two numbers, A1 and A2. And in each turn, a player can do one of these things. A player can either change A1 to one of the numbers that is smaller than A1. So 0, 1, so on to A1 minus 1. Or they can change A2, decrease A2 basically to 0, 1, all the way to A2 minus 1. Or let's say that they can decrease both of them by the same amount. So, or change A1, A2 to A1 minus X and A2 minus X. For some X that is at least 1 and at most the minimum of A1 and A2. Okay. So as soon as I add a move like this, I can no longer talk about the product of two graphs. Because now what I'm doing to A1 and A2 is not really independent. Okay. Who wants to play this game with me? Let's do it like this, 11 and 9. You see, there is a problem here. The problem is that if you use the same technique as in NIM, if you do 9, 9, I immediately win. Because now I have this rule. I can change, I can decrease both of them by the same amount. So your goal is to not give me two equal numbers. Unless they're both zero, of course. That's fine. Giving me two zeros is fine. Okay. We're running out of time. Find the winning and losing sets for this game. So this is your exercise. Find L and W. Okay, in the afternoon session, we're going to talk about a completely different type of game.